On October 29, 2025, something impossible happened 203 million kilometers from Earth. A comet-sized object from another solar system travelling at 68 kilometers per second passed closer to our Sun than Mercury ever ventures. And then, in the hours that followed, it did something that shouldn't happen. Something that violates every predictable pattern we've documented in 3 centuries of observing comets. It accelerated. Not toward the Sun, which would make sense. Not away from it in a straight line, which would also make sense. It accelerated sideways, deviating from its expected trajectory by roughly 10 times the diameter of the Earth itself. NASA documented it. The Naval Research Laboratory confirmed it. Harvard astrophysicists analysed the data and couldn't reconcile it with natural behaviour. But here's what almost no one is talking about. What this acceleration means, why it happened precisely at perihelion, and why the object's physical characteristics changed in ways that have never been observed in any comet, anywhere, ever. This isn't speculation. This is measurement. Hard data collected by multiple spacecraft, verified by institutions across 3 continents, and now sitting in scientific databases waiting for someone to explain how an interstellar visitor defied gravitational prediction in a way that suggests something far stranger than outgassing or thermal jets. Let me be clear about what we're examining here. This isn't about chasing headlines or feeding conspiracy theories. This is about looking at documented scientific observations that don't fit the models we've relied on for generations. When an object accelerates in a direction that can't be explained by solar radiation pressure, and when that acceleration coincides with visual changes that have no precedent in comet science, we have an obligation to ask uncomfortable questions, not because we want sensational answers, but because the data demands explanation. Think about what acceleration means in deep space. There are only a handful of forces that can push an object off its predicted course. Gravity from massive bodies accounted for, solar radiation pressure calculated and insufficient to explain this deviation. Outgassing from volatile materials vaporizing as the object heats up. This is the go-to explanation, and it works for most comets. Except when you run the numbers on 3i Atlas, the outgassing required to produce this specific acceleration would have stripped away roughly 10% of the object's total mass in a matter of months. That's not normal comet behaviour. That's catastrophic disintegration. And yet, the object didn't disintegrate. It didn't fragment. It didn't leave behind the debris field you'd expect from that level of mass loss. Instead, it did something even stranger. It turned blue. Not metaphorically, not slightly. It became bluer than the Sun itself, according to spectroscopic measurements taken during its closest approach. Comets don't do that. They reflect sunlight in predictable wavelengths based on their composition: dust, rock, frozen gases. Blue light at that intensity suggests something generating heat at temperatures that exceed what solar heating alone should produce. Now, I know what you're thinking. You're thinking, there's got to be a rational explanation. Scientists have seen thousands of comets. They know how this works. And you're right, they do know how this works, which is precisely why what happened on October 29th has triggered such intense scrutiny. Because the people analysing this data are the same experts who've spent decades studying cometary behaviour, and they're the ones pointing out that the pattern doesn't fit. Dr. Carl Battams, who leads the Sun-Grazing Comets project at the Naval Research Laboratory, has been tracking objects near the Sun for over 20 years. When he describes the brightness surge and the acceleration anomaly in 3i Atlas, he uses careful language, but he doesn't dismiss it. Qicheng Jiang, the astronomer at Lowell Observatory who first characterized the object's trajectory, has noted that the non-gravitational forces at play here exceed what standard models predict. And then there's Avi Loeb, chair of Harvard's astronomy department, and one of the most cited astrophysicists in the world, who's been analysing interstellar objects for years, and has openly stated that if this acceleration came purely from outgassing, we should be seeing evidence we're not finding. So here's where we are. An object from another solar system confirmed interstellar origin, based on its hyperbolic trajectory, approached our Sun, exhibited behaviour that doesn't match natural comet dynamics, accelerated in a direction that implies some form of thrust or propulsion, turned an unprecedented shade of blue, and is now heading back out into deep space carrying answers we don't have. This isn't the first interstellar visitor we've detected. In 2017, 1I Oumuamua passed through our solar system and baffled scientists with its elongated shape and unexplained acceleration. In 2019, 2I Borisov arrived a more conventional comet that behaved exactly as models predicted, which was almost a relief. It was normal, familiar. And then came 3I Atlas in 2024, discovered while still approaching, giving us months to study it before perihelion, months to prepare instruments, calculate trajectories, predict behaviour. And despite all that preparation, despite all that lead time, it still surprised us. 3 interstellar objects in 8 years, each one different, each one telling a different story about what's out there beyond the boundary of our solar system. But 3I Atlas is the only one that accelerated at perihelion in a way that can't be easily reconciled with natural processes. That's the part that demands attention. Before we go further, I need you to do something. Hit the like button if you want to see where this evidence leads, not because you've already decided what this object is, but because you want to examine the data with clear eyes and draw your own conclusions. This is the kind of story that gets buried under headlines about celebrity gossip and political theatre, but it's also the kind of story that, decades from now, might be remembered as the moment we started asking the right questions. So don't let this disappear into algorithmic obscurity. Engage with it. Share it. Make sure people actually see what the data shows. What you're about to hear isn't wild speculation dressed up as science. It's the opposite. It's a careful, methodical walk through every major observation made during 3I Atlas's perihelion passage, the measurements, the deviations, the competing theories proposed by actual astrophysicists. And by the end, you'll understand why some scientists are comfortable saying, this is unusual comet behaviour, while others are willing to entertain the possibility that what we witnessed on October 29th might represent something we've never encountered before. Because here's the uncomfortable truth that sits beneath all of this. We don't actually know what most interstellar space looks like. We've never sent a probe beyond the heliopause that's done more than scratch the surface. We have theories about what's normal out there, but those theories are built on a sample size of exactly 3 confirmed interstellar objects. 3. That's not enough data to declare anything impossible. It's barely enough to establish a pattern. So when an object from that uncharted territory does something unexpected, something that falls outside the narrow band of behaviours we've observed, we have 2 choices. We can force it into the boxes we already understand, even if the fit is uncomfortable. Or we can let the mystery be a mystery long enough to gather better data. That's where we are now. Gathering. Measuring. Watching as this object continues its journey away from our sun, carrying with it the evidence of what happened during those critical hours around perihelion. But to understand what that evidence means, we first need to understand what we're comparing it to. We need to look at the other visitors, the ones that came before, and see exactly why 3I Atlas is different. Let's establish something fundamental. Before 2017, we had never confirmed the detection of an object from outside our solar system passing through our neighbourhood. Not once. For all of human history, every comet, every asteroid, every piece of space debris we'd ever observed originated from within the sun's gravitational influence. We theorized that interstellar objects must exist statistically. They had to, but we'd never actually caught one in the act of passing through. Then on October 19th, 2017, a telescope in Hawaii spotted something strange. An object moving too fast, on a trajectory too steep, with an orbital eccentricity that was off the charts. They named it 1A Nziu Oumuamua, which roughly translates to scout or messenger in Hawaiian, and it was exactly that, a messenger from another star system, confirming that the space between stars isn't empty. It's populated with debris, rocks, frozen remnants from planetary systems we'll never see. Oumuamua was bizarre from the start. It was elongated, shaped like a cigar or a pancake, depending on which analysis you believe, and it tumbled through space in a way that made determining its exact dimensions nearly impossible. But the strangest thing wasn't its shape, it was the acceleration. As Oumuamua sped away from the sun, it accelerated slightly faster than gravity alone could explain. Not by much, just enough to be measurable, enough to be undeniable. Scientists scrambled for explanations. The leading theory was outgassing frozen gases vaporizing as the object heated up, creating tiny jets that pushed it off course like a leaky balloon. Except there was a problem. Outgassing produces a visible coma, a cloud of gas and dust surrounding the object, and Oumuamua didn't have one. No coma, no tail, no detectable emissions, just acceleration with no visible cause. That's when Avi Loeb proposed something that made headlines and divided the scientific community. What if Oumuamua wasn't entirely natural? What if it was a light sail, a thin, reflective sheet propelled by starlight, or even a defunct piece of alien technology drifting through space? He wasn't saying it was definitely artificial. He was saying the data didn't rule it out, and that we shouldn't ignore uncomfortable possibilities just because they sound like science fiction. The backlash was immediate. Other astronomers pushed back hard, arguing that extraordinary claims require extraordinary evidence, and that Oumuamua's behaviour could still be explained by natural processes we hadn't fully considered. Outgassing from hydrogen ice. Nitrogen ice behaving in unusual ways. There were models that fit, even if they required stretching assumptions. Then, in August 2019, we got our second visitor. 2I Borisov. And this one was refreshingly normal. It looked like a comet. It acted like a comet. It had a visible coma, a tail outgassing that matched predictions. Its composition resembled comets from our own Oort cloud water ice, carbon monoxide, dust. It followed the expected trajectory with no mysterious accelerations, no unexplained anomalies. Scientists could point to Borisov and say, "See, this is what an interstellar comet looks like. This is normal." And it was. Borisov behaved exactly as theory predicted, which was almost comforting after the chaos of Oumuamua. It suggested that most interstellar objects would be unremarkable, just frozen debris from other star systems, chemically similar to our own comets, passing through on hyperbolic orbits before disappearing back into the void. For 5 years, those were our only reference points. 2 objects, one weird, one normal, a sample size too small to draw meaningful conclusions. And then came 3I Atlas. It was detected in late 2024, still, far from the Sun, giving astronomers time to study it during its approach. Early observations suggested it might be another Borisov, a conventional interstellar comet with predictable behaviour. Its orbital eccentricity was calculated at 6/145, meaning its path was extremely hyperbolic. It wasn't bound to the Sun. It came from somewhere else, and it would leave, never to return. But there was something unusual about its trajectory from the start. It was travelling retrograde, moving in the opposite direction to the planet's orbits. That's not unheard of, but it's uncommon. And its velocity at infinity, the speed it would eventually reach once free of the Sun's gravity, was calculated at roughly 58 kilometers per second. Fast. Faster than Borisov. Faster than most long-period comets originating from our own Oort cloud. Still, none of that was alarming. Retrograde orbits exist. High velocities exist. What mattered was how it would behave as it approached perihelion, the point of closest approach to the Sun. That's where comets reveal their true nature. That's where the heat triggers outgassing, where brightness increases, where we get spectroscopic data to analyse composition. So astronomers watched, they calculated, they predicted exactly where 3I Atlas should be at every stage of its approach, accounting for gravitational influences from the Sun and major planets. They built models that forecasted its brightness curve, its outgassing rate, the trajectory it should follow after perihelion. And then October 29th arrived. What happened next didn't match the models. The object brightened far more rapidly than predictions allowed. It exhibited non-gravitational acceleration, meaning forces other than gravity were affecting its path. And that acceleration wasn't small or subtle. It was significant enough that within weeks of perihelion, the object had deviated from its expected position by roughly 10 times the diameter of Earth. That's not a rounding error. That's a massive deviation that requires explanation. Comets accelerate all the time due to outgassing. This isn't controversial, but the magnitude of this acceleration, combined with the direction of the deviation and the lack of proportional debris, created a pattern that didn't fit standard comet behaviour. Qicheng Jiang noted the anomaly. Carl Battams confirmed the brightness surge exceeded expectations. Avi Loeb started running calculations on what the mass loss rate would need to be to produce this acceleration naturally, and the numbers were staggering. Here's what makes 3I Atlas different from both of its predecessors. Oumuamua had mysterious acceleration but no visible outgassing and an unusual shape. Borisov had normal behaviour and matched expectations perfectly. 3I Atlas has significant acceleration, rapid brightness increases spectroscopic anomalies, and yet it's not fragmenting or disintegrating the way an object should if it's losing mass at the rate required to produce this. Thrust. 3 interstellar visitors, 3 completely different profiles, And the third one, the one we had the most time to study, the one we thought we'd understand, turned out to be the most confusing. That's where we are. Not because scientists are hiding something, but because the data from October 29th presents a puzzle that doesn't have an obvious solution. To understand why, we need to go back to the weeks before perihelion to the approach, when 3i Atlas began to wake up. There's a moment in every comet's journey when it stops being a frozen rock and starts becoming active. It's called the sublimation threshold, the distance from the Sun where surface ice begins to vaporize. For most comets, this happens somewhere beyond the orbit of Jupiter, when solar radiation finally carries enough energy to turn frozen volatiles directly into gas without passing through a liquid phase. Water ice, carbon dioxide, methane, ammonia. These molecules sit dormant for millennia in the frozen darkness between stars, and then, suddenly, the Sun's warmth reaches them and they begin to stir. 3i Atlas crossed that threshold in early 2025, still millions of kilometers from perihelion. Ground-based telescopes and space-based observatories began detecting the telltale signs of cometary activity, a faint coma forming around the nucleus, a slight brightening as sunlight reflected off gas and dust particles being released. This was expected. This was normal. Comets from our own Oort cloud do this. Borisov did this. There was no reason to think 3i Atlas would behave any differently. As the weeks passed and the object drew closer to the Sun, the activity increased. Water vapor was detected. Spectroscopic analysis confirmed the presence of H2O molecules in the coma, matching the signature of ice vaporizing from the surface. The brightness continued to climb, following a predictable curve that fit cometry models. Instruments aboard STEREOA and SOHO spacecraft, designed specifically to monitor the Sun and objects near it, tracked 3i Atlas as it approached, cataloguing every measurable change. By mid-October, the object was bright enough to be visible in amateur telescopes from certain locations on Earth. Astrophotographers captured images showing a distinct coma and the beginnings of a tail material streaming away from the nucleus under pressure from solar wind and radiation. Everything about this early phase suggested we were watching a typical interstellar comet, doing exactly what comets do. The heat was building, the ice was vaporizing, the object was responding to solar energy in ways that matched 3 centuries of observational data. But here's what you need to understand about cometary outgassing. It's predictable. We know how much energy the Sun delivers at any given distance. We know the sublimation temperatures of various ices. We can calculate with reasonable accuracy how much mass a comet should lose per hour based on its size, composition, and distance from the Sun. These aren't wild guesses, they're physics, heat transfer, thermodynamics, equations that work the same whether the comet originated in our solar system or travelled from another star. When a comet approaches perihelion, the outgassing intensifies. This creates what's called a jet, a concentrated stream of gas and dust erupting from the surface, usually from areas where the ice is most exposed or where internal pressure is built up beneath a thin crust. These jets are visible in high-resolution images as bright plumes extending from the nucleus, and they're the primary mechanism by which comets accelerate beyond what gravity alone would predict. The direction of these jets matters. If they erupt from the sunward side of the nucleus, they push the comet slightly away from the Sun. If they erupt from the night side, they push it toward the Sun. If they erupt asymmetrically due to the comet's rotation, they create sideways thrust that alters the trajectory in more complex ways. But in every case, every documented case in the history of comet science, the magnitude of the acceleration matches the visible outgassing. You can see the jets, you can measure the gas production rate, you can verify that the thrust being generated is proportional to the mass being expelled. As October wore on, and 3i Atlas closed the final distance to perihelion, the outgassing should have reached its peak. Models predicted a sharp increase in brightness, a dramatic expansion of the coma, possibly even fragmentation if internal stresses became too great. Comets are fragile. They're not solid rocks, they're loose aggregates of ice and dust barely held together by weak gravity. When they get close to the Sun, the thermal stress can rip them apart. It happens all the time. So researchers prepared for multiple scenarios. Maybe 3i Atlas would hold together and emerge from perihelion intact like Borisov. Maybe it would fragment into several pieces like many sun-grazing comets observed by SOHO over the years. Maybe it would disintegrate entirely, leaving behind only a debris field essentially vaporizing in the Sun's heat. What they didn't prepare for, what the models didn't predict, was what actually happened. On October 29th, as 3I Atlas reached perihelion at a distance of 203 million kilometers from the Sun, something changed. The brightness didn't just increase, it surged, not over days, but over hours. The spectroscopic signature shifted in ways that couldn't be explained by standard outgassing alone, and the object began to accelerate. Now, let me pause here and clarify what acceleration means in this context, because it's easy to misunderstand. All objects near the Sun accelerate. Gravity pulls them faster as they get closer, just like a ball rolling down a hill speeds up as it descends. That's gravitational acceleration, and it's entirely predictable. You can calculate it using Newton's laws, accounting for the Sun's mass, the object's velocity, and the distance between them. This is not mysterious. This is high school physics. But non-gravitational acceleration is different. That's when an object speeds up or changes direction in ways that gravity alone can't explain. For comets, this almost always comes from outgassing jets pushing the comet off its predicted path. And yes, we expected 3I Atlas to exhibit non-gravitational acceleration. Borisov did. Most active comets do. The question wasn't whether it would accelerate, it was how much, and whether that acceleration would match the visible outgassing. Here's the problem. The acceleration observed in 3I Atlas was stronger than what the visible coma and brightness suggested. Qicheng Jiang, who was tracking the object's trajectory with high precision, noted that the deviation from the predicted path was significant, far more than the modest outgassing activity seemed to warrant. It was as if something was pushing the object harder than the jets alone could account for. Carl Battams, monitoring the object through SOHO's instruments, saw the same thing. The brightness surge was anomalous. Comets brighten as they approach the Sun, that's normal. But the rate of brightening, the intensity of the peak, and the spectroscopic characteristics were all slightly off from what standard models predicted for an object of this size and composition. And then there was the colour. Most comets, when observed spectroscopically, reflect sunlight in a way that reveals their composition. Dust-heavy comets appear reddish. Gas-rich comets appear whiter. The exact colour depends on the mixture of materials and how they scatter light. But 3I Atlas did something unusual. At perihelion it turned blue, not just a slight blue tint, measurably bluer than the Sun itself in certain wavelengths. Blue light at that intensity suggests heat. Specific types of molecules like CO+, ionized carbon monoxide, glow blue when excited by ultraviolet radiation. But the degree of blueness observed in 3I Atlas suggested temperatures higher than what solar heating alone should produce at that distance. It was as if the object was generating additional heat or reflecting light in a way that concentrated blue wavelengths beyond normal expectations. None of these observations, taken individually, would be enough to call the object anomalous. Comets surprise us all the time. They outgas more than predicted or less. They fragment unexpectedly. They develop unusual comas. Cometary science is full of edge cases that don't fit perfectly into models because comets are chaotic, loosely bound piles of ice and rock, subject to forces that vary wildly depending on their internal structure. But when you take all of these observations together, the excessive brightness surge, the significant non-gravitational acceleration, the blue colour shift, the lack of proportional debris, the pattern stops looking like normal variability and starts looking like something else. Something that requires explanation beyond comets are unpredictable. And that's where we were on October 30th, the day after perihelion. Staring at data that didn't quite fit. Watching an interstellar visitor accelerate away from the Sun in a manner that left scientists scrambling to reconcile observations with theory. The object was moving now, continuing its journey back into deep space, but the questions it raised were just beginning. Because what happened at perihelion wasn't just unusual, it was the kind of unusual that demands follow-up. That requires scrutiny, that forces scientists to choose between expanding their models or reconsidering their assumptions, and that's exactly where we're about to go. Perihelion is the moment of truth for any comet. It's the point of maximum stress, maximum heat, maximum activity. Everything that's been building during the approach, the sublimation, the outgassing, the structural strain reaches its peak in the hour surrounding closest approach to the Sun. For researchers, it's the single most valuable observation window. You get spectroscopic data at maximum brightness. You measure the outgassing rate at its highest. You watch how the object responds to extreme thermal stress. And from that data, you can determine composition, structure, origin, essentially everything that makes the comet what it is. For 3I Atlas, perihelion occurred on October 29, 2025, at a distance of 1.36 astronomical units from the Sun, about 203 million kilometres. That's closer than Mars orbits, but farther out than Earth. It's not an extreme perihelion by comet standards. Plenty of comets pass far closer, diving within the orbit of Mercury, sometimes skimming just above the Sun's surface. At 136 AU, the solar radiation is intense, but not catastrophically so. Comets survive these conditions routinely. What makes the October 29th observation significant isn't the distance, it's what the object did at that distance. Let's start with the brightness. In the weeks leading up to perihelion, 3I Atlas followed a brightness curve that matched predictions. It was getting brighter as it approached, exactly as models forecasted based on its size and assumed composition. Then, within hours of perihelion, the brightness spiked. Not gradually suddenly. The magnitude increased far more than the distance change alone could explain. It was as if something triggered a massive release of gas and dust in a very short time frame. Carl Battams, who has observed thousands of comets through SOHO instruments, described the brightness behaviour as unusual but not unprecedented. Comets occasionally undergo outbursts, sudden increases in activity caused by subsurface pockets of volatile ice breaking through the surface crust. These outbursts can temporarily make a comet several times brighter than expected, so a brightness spike on its own isn't alarming. It's within the range of known comet behaviour. But here's where it gets complicated. The brightness spike coincided with measurable changes in the object's trajectory. Within days of perihelion, trajectory refinements showed that 3I Atlas was not where it was supposed to be. The deviation was small in absolute terms, thousands of kilometres, but significant relative to the precision of orbital predictions. Something had pushed it off course. Non-gravitational acceleration is the term astronomers use when an object's path deviates from pure gravitational motion. And again, this is normal for active comets. Outgassing creates thrust. But the magnitude of the deviation in 3I Atlas required a specific amount of thrust, a calculable force based on the object's estimated mass and the observed change in velocity. And when Avi Loeb ran those calculations, he arrived at a troubling conclusion. According to Loeb's analysis, if this acceleration came from outgassing alone, the object would need to shed roughly a tenth of its mass in just a few months. That's a testable prediction. ESA's JUICE spacecraft will be able to detect this in November. But here's the thing, mainstream comet experts like Carl Battams propose the outgassing explanation while acknowledging the brightening rate remains unexplained by standard models. Think about what 10% mass loss means. Imagine a city block-sized object roughly the estimated size of 3I Atlas losing 10% of its volume in a matter of weeks. That's not gentle sublimation, that's explosive disintegration. You wouldn't expect the object to hold together, you'd expect fragmentation, a massive debris cloud, visible structural collapse, and yet, observations showed none of that. The object remained intact. No fragmentation events were reported, no debris field trailing behind. The coma expanded, yes, but not in a way that suggested catastrophic mass loss. It looked, from a distance, like normal outgassing, except the acceleration implied it wasn't normal at all. This is the core problem. The visible activity didn't match the implied thrust. It's like watching a car accelerate down a highway at 100 miles per hour, while the engine sounds like it's barely idling. The numbers don't reconcile. Loeb has been careful in how he frames this. He's not claiming 3I Atlas is definitely artificial. He's saying that if we assume purely natural outgassing, we arrive at mass loss rates that should produce observable consequences we're not seeing. That discrepancy means either our mass estimates are wrong, or our understanding of cometary outgassing is incomplete, or something else is contributing to the acceleration beyond standard volatile sublimation. And then there's the colour issue. Spectroscopic observations taken during perihelion showed that 3I Atlas was reflecting and emitting light with an unusual blue component. Specifically, wavelengths in the blue end of the visible spectrum were more intense than expected. The most common explanation for blue coloration in comets is ionized carbon monoxide CO+, molecules glowing blue when struck by ultraviolet light from the sun. This happens in many comets, it's normal. Except the intensity was abnormal. The object appeared bluer than the sun itself in certain measurements, suggesting either an unusually high concentration of CO+, or additional heating that enhanced the emission beyond what solar UV alone should produce. Some researchers suggested it could be due to the object's composition, Maybe it was unusually rich in carbon monoxide compared to water, which would skew the colour signature. Others pointed out that the blue intensity peaked right around perihelion, which is exactly when thermal stress would be highest. But if the blue colour was purely thermal, caused by the object heating up that would require internal temperatures higher than what surface heating alone should produce. Comets don't have internal heat sources. They're cold, inactive ice balls until the sun warms them from the outside. The heat propagates inward slowly, sublimating ice layer by layer. You don't get deep internal heating unless something else is generating energy. So what could generate energy inside an interstellar comet? Radioactive decay is one possibility. Certain isotopes embedded in the object's interior could release heat over time, but the amount of radioactive material needed to produce observable heating would be enormous, and we have no evidence that interstellar objects are significantly more radioactive than solar system comets. Another possibility is tidal heating gravitational stress from the sun squeezing and flexing the object as it passes close by. This happens with Jupiter's moon Io, which is volcanically active because Jupiter's gravity constantly deforms its interior. But 3I Atlas passed at 1.36 AU, far enough that tidal forces from the sun would be negligible. Not zero, but nowhere near enough to generate significant heating. Which brings us to the third possibility, the one that Avi Loeb has explored in his research: artificial heating, a propulsion system, a heat source that isn't natural. He's careful to frame this as a hypothesis, not a conclusion. He's not saying this is an alien spacecraft. He's saying, if the natural explanations don't fully account for the observations, we shouldn't dismiss technological explanations just because they sound implausible. This is where mainstream scientists push back hard. The burden of proof for extraordinary claims is extraordinarily high. If you're going to propose that an interstellar object might be artificial, you need more than gaps in natural explanations. You need positive evidence of artificiality. And right now, that evidence doesn't exist. There's no radio signal, no geometric structure, no detectable machinery. Just anomalies that could, with some creative modelling, still fit within natural processes. But here's what makes this moment different from past debates about interstellar objects. We have time. Unlike Oumuamua, which was discovered on its way out of the solar system and was gone before we could study it properly, 3I Atlas is still within observational range. It's moving away from the sun, yes, but it's not gone. Telescopes can still track it, spacecraft can still observe it, and as it moves farther from the sun and cools down, we'll be able to measure whether the outgassing decreases, whether the brightness fades, whether the acceleration continues or stops. Those future observations will matter enormously. If the acceleration stops once the object cools, if it returns to a purely gravitational trajectory, that would strongly support the outgassing hypothesis. It would suggest that whatever thrust was observed at perihelion was purely thermal, driven by solar heating, and naturally ceases as the object recedes. But if the acceleration continues, even slightly, after the object has cooled beyond the point where outgassing should be significant, that would be far harder to explain naturally. It would suggest a force that isn't tied to solar heating, a force that persists independent of distance from the sun. That's the test. That's what we're watching for in the coming weeks and months. Does 3I Atlas behave like a comet should once it's past perihelion, or does it continue to surprise us? And there's another test coming. Here's what we can't see yet: the debris field. And that's the actual test, because Earth-based telescopes can't peer through the sun's glare. But in December, when 3I Atlas emerges from behind the sun, we'll have direct visibility. If Loeb is right about artificial propulsion, there will be no massive debris cloud. If the mainstream theory is correct, the debris field will be massive and unmistakable. In other words, December 19th isn't just 3I Atlas's closest approach to Earth. It's the moment both theories get tested. For now, we're left with data that doesn't quite fit, observations that point in multiple directions, scientists arguing over interpretations, which is exactly what they should be doing. Science advances by testing competing hypotheses against evidence, not by declaring premature consensus. So let's look at those competing hypotheses directly. What are the two main explanations for what happened on October 29th? What does each theory predict and where do they struggle? Because understanding the debate isn't just academic, it's the key to interpreting what happens next. When something unexpected happens in space, scientists do what they always do. They build models. They take the observations, run them through equations, and see which explanations fit the data. For 3i Atlas, two dominant theories have emerged, each with its own set of supporting evidence, each with its own problems, and the tension between them is what makes this object so fascinating. Let's start with the conventional explanation, natural outgassing. This is the default hypothesis for any cometary acceleration, and it's grounded in well-understood physics. Comets are made of volatile ices, water, carbon dioxide, carbon monoxide, methane, ammonia, all frozen solid in the cold of interstellar space. When a comet approaches the Sun, solar radiation heats the surface, and those ices begin to sublimate, turning directly from solid to gas without melting. The gas expands rapidly, creating pressure that lifts dust particles off the surface and forms the characteristic coma and tail we associate with comets. But sublimation doesn't happen uniformly across the entire surface. Comets rotate, so some areas face the Sun while others are in shadow. The sunlit side heats up faster, sublimates more ice, and produces more gas. This creates jets, concentrated streams of vapor erupting from specific points on the surface, and those jets generate thrust. It's basic action-reaction physics. Gas shooting out in one direction pushes the comet in the opposite direction. This process is called the rocket effect, and it's been observed in hundreds of comets. It's not mysterious. It's not controversial. It's how comets naturally accelerate beyond what gravity predicts. The question isn't whether outgassing can cause acceleration, it's whether outgassing alone can account for the magnitude and direction of the acceleration observed in 3i Atlas. Carl Battams and other mainstream comet researchers argue that yes, outgassing is sufficient to explain the data. They point out that 3i Atlas exhibited all the signs of an active comet, a visible coma. Brightness increases consistent with gas and dust production. Spectroscopic signatures of water vapor and carbon monoxide. The acceleration, while larger than initially expected, isn't outside the realm of possibility if you adjust assumptions about the object's mass, composition, or internal structure. Maybe 3i Atlas is less massive than early estimates suggested, which would mean less thrust is needed to produce the observed acceleration. Maybe it's unusually rich in volatile ices, allowing for more vigorous outgassing than typical comets. Maybe its rotation axis is oriented in a way that concentrates jet activity, creating asymmetric thrust that amplifies the acceleration. These are all reasonable adjustments. They don't require new physics or exotic materials. They just require that 3i Atlas be somewhat different from the average comet. And we already know it's different because it came from another star system. Interstellar objects formed under different conditions, in different environments, around stars with different compositions. It would be stranger if they were identical to solar system comets than if they showed some variability. Chicheng Jiang, who calculated the object's trajectory and noted the non-gravitational forces, has also suggested that the acceleration could be explained by volatilaric composition. If 3i Atlas contains more frozen carbon monoxide relative to water than typical comets, it would sublimate more easily at greater distances from the Sun, producing thrust earlier and more intensely than water-dominated comets. This would account for both the blue color signature CO+ emissions and the stronger than expected acceleration. So the outgassing hypothesis has merit. It fits most of the observations. It doesn't require invoking anything we don't already understand, and scientifically, that's valuable. Occam's razor suggests we should prefer the simplest explanation that accounts for the data. But there are gaps, problems that don't quite resolve, even with the adjustments. First, the mass loss issue. If you calculate how much gas needs to be expelled to produce the observed acceleration, you arrive at mass loss rates that should leave behind a visible debris field dust, particles, fragments shed from the nucleus as the ice sublimates. And while there is a coma around 3i Atlas, it's not proportionally massive. The debris cloud you'd expect from that level of outgassing should be larger, brighter, more diffuse. It should persist as the object moves away from the Sun, gradually dispersing into space. We're not seeing that, at least, not yet. Second, the direction of acceleration. Outgassing thrust depends on where the jets are located and how the comet is rotating. If the jets are symmetrically distributed, they cancel out and produce no net acceleration. If they're asymmetric, they push the comet off course. But the specific direction of the acceleration in 3i Atlas, the deviation from the predicted trajectory, doesn't align perfectly with what you'd expect from random jet orientations. It's possible to construct a model where the jets are positioned just right to produce this effect, but it requires fine-tuning the parameters in ways that feel slightly forced. Third, the blue colour intensity. Yes, CO+ glows blue. Yes, comets emit CO+. But the degree of blueness observed at perihelion was on the high end of what standard models predict. It's not impossible, it's just unusual. And when you stack one unusual observation on top of another, the cumulative improbability starts to weigh on you. Which brings us to the alternative hypothesis: artificial acceleration. Avi Loeb has spent years studying interstellar objects and technosignatures, evidence of advanced civilizations. His work on Oumuamua brought this perspective into the mainstream, and he's applying the same rigorous approach to 3I Atlas. He's not claiming it's definitely artificial. He's asking whether the data excludes that possibility, and arguing that it doesn't. Here's the logic. If 3I Atlas were equipped with some form of propulsion system, a light sail, a solar-powered engine, even a passive reflective surface designed to harness solar radiation pressure, it could accelerate without producing the massive outgassing plume that natural processes require. The acceleration would still need an energy source, but that source wouldn't necessarily be volatile ice sublimating from the surface. A light sail, for example, uses photons from the sun to generate thrust. Sunlight carries momentum, and when photons reflect off a large, thin surface, they transfer that momentum to the object, pushing it away from the sun. This is real physics. NASA has tested light sail technology on spacecraft like LightSail 2. It works. The thrust is tiny, but over time it adds up. An interstellar probe equipped with a light sail could theoretically accelerate using sunlight alone without any onboard fuel or outgassing. But here's the problem. Light sails produce acceleration away from the sun, not sideways. Solar radiation pressure always pushes directly outward from the sun, because photons travel in straight lines. If 3I Atlas were a light sail, its acceleration should be radial directly away from the sun, along the line connecting them. Instead, the observed acceleration included a tangential component sideways motion relative to the expected orbit. That doesn't rule out a sail, but it complicates the explanation. You'd need the sail to be angled, or rotating, or asymmetrically reflective in ways that redirect the thrust. It's possible spacecraft use angled sails all the time to adjust their trajectories, but it requires assuming the object has some form of attitude control, some way of orienting itself to steer. And if you're already assuming attitude control, you're no longer talking about a passive object drifting through space. You're talking about something with functional systems, something designed to navigate, something potentially intelligent, or at least built by intelligence. Loeb is careful to frame this as speculative. He emphasizes that without direct evidence, radio signals, geometric structures, materials that couldn't form naturally, we can't confirm artificial origin. But he also argues that dismissing the possibility prematurely is unscientific. If the data doesn't fully fit natural models, we should explore alternatives, even uncomfortable ones. The scientific community is divided on this. Some researchers appreciate Loeb's willingness to think outside conventional boundaries, to ask questions that others avoid because they sound too much like science fiction. Others argue that he's giving too much weight to anomalies that will likely resolve once we have better data or refine our models. Both perspectives have merit. Science advances by challenging assumptions, but it also advances by not chasing every anomaly as if it's revolutionary. The trick is knowing when an anomaly is significant enough to justify extraordinary hypotheses and when it's just noise in the data. Right now, we're in that grey zone. The observations are unusual, but not definitively beyond natural explanation. The gaps in the outgassing model are real, but they might close with better measurements. The artificial hypothesis is interesting, but it lacks direct supporting evidence. So where does that leave us? With two competing explanations, neither fully satisfying, and a set of future observations that will help tip the balance. If the object continues to behave like a comet, as it moves away from the sun, fading in brightness, ceasing acceleration, leaving a debris trail, the outgassing hypothesis wins. If it does anything else, the mystery deepens, and that's exactly why the next 60 days matter so much. Because the data we collect now, while 3I Atlas is still observable, will determine which theory survives and which collapses. This isn't speculation anymore, it's testable science with clear predictions and measurable outcomes. But before we look forward, we need to address the elephant in the room. What aren't we being told? What data exists that hasn't been emphasized in public discussions? Because there's always more to the story than the headlines reveal. Let me be clear about something right from the start. This isn't a section about conspiracy theories or hidden cover-ups. NASA isn't concealing data. The Naval Research Laboratory isn't hiding observations. Scientific institutions aren't engaged in coordinated suppression of evidence. That's not how modern astronomy works. Observations are published. Data is shared across international networks. Peer review is public. If you want to examine the raw measurements from Stereo A or SOHO, you can access those databases yourself. But here's what is true. Emphasis matters. The way information is presented, the aspects that get highlighted in press releases versus buried in technical papers, the questions that get asked versus the ones that get sidestepped, all of that shapes public perception. And when it comes to 3i Atlas, there are elements of the story that aren't making it into mainstream coverage. Not because they're being suppressed, but because they complicate the narrative. Because they raise questions that don't have satisfying answers yet. So let's talk about what's not being emphasized. First, the trajectory deviation isn't small. When I mentioned earlier that 3i Atlas deviated by roughly 10 times Earth's diameter, that's 127,000 kilometers. That's not a subtle drift caused by measurement uncertainty. That's a massive positional discrepancy that required significant force over an extended period to produce. And the fact that this deviation occurred specifically during and immediately after perihelion, when the object was at maximum stress, and activity suggests the acceleration wasn't constant. It spiked. Something happened at closest approach that amplified the non-gravitational forces far beyond what was observed during the approach phase. Most news coverage mentions the acceleration in passing, framing it as expected comet behaviour. And technically, that's true, comets accelerate. But the magnitude isn't being communicated clearly. The public hears acceleration and assumes it's a minor adjustment, a rounding error in orbital mechanics. It's not. It's substantial enough that trajectory prediction models had to be completely recalculated after perihelion, because the object wasn't where the pre-perihelion model said it would be. Second, the debris field is missing. Here's what we can't see yet. The debris field, and that's the actual test. Because Earth-based telescopes can't peer through the sun's glare. But in December, when 3i Atlas emerges from behind the sun, we'll have direct visibility. If Loeb is right about artificial propulsion, there will be no massive debris cloud. If the mainstream theory is correct, the debris field will be massive and unmistakable. In other words, December 19th isn't just 3i Atlas's closest approach to Earth, it's the moment both theories get tested. When a comet sheds 10% of its mass through outgassing, you don't just see a faint coma, you see a dense, expanding cloud of dust and particles trailing behind the nucleus, persisting for weeks or months as the material slowly disperses. That debris reflects sunlight and should be detectable by sensitive instruments, even at great distances. So far, we haven't seen that. The coma exists, but it's not the massive debris field that the implied mass loss rate would produce. Now, it's possible we're just not looking at the right wavelengths, or the debris is smaller than detection thresholds, or it's distributed in ways that make it harder to observe. But the absence of a prominent debris trail is notable, and it's not being discussed much in mainstream coverage. Third, the colour shift wasn't gradual. The blue spectral signature appeared suddenly at perihelion and persisted for a relatively short window. If the blue colour were purely due to CO+ emissions from outgassing, you'd expect it to correlate smoothly with brightness. As the object gets more active, the emissions increase, the colour shifts. But the spectroscopic data shows a sharp transition, as if something activated at perihelion that wasn't active before. That sharp transition is unusual. It's the kind of pattern you'd expect from a threshold event, something that triggers when specific conditions are met, like internal ice reaching a critical temperature, or a structural failure that suddenly exposes fresh volatileric material. Or, if you're entertaining alternative hypotheses, it's the kind of pattern you'd see if a propulsion system activated at closest approach when solar energy availability peaked. Fourth, there's an observational gap. For a brief period around perihelion, 3i Atlas was too close to the sun in the sky to be observed from Earth. The glare made it impossible for ground-based telescopes to track it continuously. Space-based instruments like Stereo and SOHO had better viewing angles, but even they have limitations. There's a window of several hours during which we have incomplete data, essentially. The object was hidden by the sun's brightness exactly when the most dramatic changes were occurring. That gap is unavoidable. It's a limitation of observing geometry, not a failure of instrumentation. But it means we don't have continuous second-by-second tracking of exactly when the acceleration began, how quickly the blue colour shift occurred, or whether there were other transient phenomena that happened and ended before we could observe them. Scientifically, that gap is frustrating because it's precisely when the most interesting physics was happening, and it leaves room for speculation, because we're stitching together observations from before and after perihelion without complete continuity. Fifth, the rotation state is poorly constrained. We don't have high-resolution images of 3I Atlas's nucleus. We don't know its exact shape, how fast it's rotating, or whether that rotation is stable or tumbling chaotically. All of those factors affect how outgassing thrust is distributed. A slowly rotating comet with jets aligned to its poles will accelerate differently than a rapidly tumbling comet with jets scattered across its surface. For Oumuamua, the lack of rotation data was a major source of uncertainty. Different rotation models led to wildly different conclusions about its shape and behaviour. We're in a similar situation with 3I Atlas. We have spectroscopic data, brightness curves, trajectory measurements, but we don't have detailed structural information. And without that, we're making educated guesses about how the object is responding to solar heating. This isn't a cover-up, it's just the reality of observing a small, distant object moving quickly through space. We're limited by telescope resolution, observing time, and the fact that 3I Atlas is only briefly bright enough to study before it fades back into obscurity. But the result is that we're working with incomplete information. And when information is incomplete, interpretations multiply. Different researchers fill in the gaps with different assumptions, leading to different conclusions. What's frustrating is that many of these gaps are solvable. We have the technology to gather better data, higher resolution spectroscopy, continuous tracking from multiple observatories, space-based missions that could rendezvous with interstellar objects if we had enough warning. The James Webb Space Telescope could provide infrared observations that reveal thermal signatures invisible to optical telescopes. ESA's Comet Interceptor mission, launching later this decade, is specifically designed to visit a new interstellar object if one is detected early enough. But 3I Atlas appeared with limited warning, and by the time resources were allocated to study it, it was already approaching perihelion. We got good data, but not perfect data. And the imperfections are where the mystery lives. So when I say evidence NASA isn't emphasizing, I'm not accusing anyone of dishonesty. I'm pointing out that the full picture is more complex than what makes it into headlines. The trajectory deviation is larger than casual coverage suggests. The debris field is missing when it shouldn't be. The color shift was abrupt and transient. The observational gaps are significant, and the structural data we'd need to definitively resolve the competing theories doesn't exist yet. All of that matters, because it means the story isn't over. The observations from October 29th raised questions that won't be answered until we have follow-up data from the coming weeks and months, and that follow-up data is what we need to talk about next because it's the key to everything. Here's where this stops being just an interesting anomaly and becomes something you can follow in real time. Because 3I Atlas isn't gone, it's not lost in the depths of space beyond our ability to observe. It's still here, still moving, still within range of Earth's most powerful telescopes, and over the next 60 days we're going to get data that either confirms the conventional explanation or deepens the mystery in ways that demand more radical theories. Let me walk you through exactly what's coming, when it's coming, and what each observation will tell us. First, November 2025 marks the re-emergence from solar conjunction. For several weeks after perihelion, 3I Atlas was too close to the Sun in Earth's sky to observe clearly. The glare overwhelmed any signal from the object itself, but as it continues moving along its trajectory, it's separating from the Sun's position on the sky, making it accessible again to ground-based telescopes. By mid to late November, observatories around the world will be able to resume tracking. What they'll be looking for is brightness. If 3I Atlas is a natural comet behaving as expected, its brightness should be fading now that it's moving away from the Sun and the outgassing is decreasing. The rate of fading will tell us how much volatile material is still being released, which in turn tells us whether the perihelion activity was a temporary spike or the beginning of sustained disintegration. If the brightness fades quickly faster than models predict, that would suggest the object exhausted a large fraction of its volatiles during the perihelion passage and is now dormant. If it fades slowly, or not at all, that would be anomalous. It would mean the object is still active despite being farther from the Sun, which would require explaining why it's retaining heat or continuing to release gas when solar energy input is decreasing. Second, December 19th, 2025 is the big one. That's when 3I Atlas reaches its closest approach to Earth, 168 million miles, or about 1.1 astronomical units. That's not particularly close by solar system standards. Mars can get closer than that during opposition, but it's close enough that Earth-based telescopes will have excellent viewing geometry. The object will be observable without interference from the Sun's glare, allowing for high-resolution spectroscopy, photometry, and astrometry. This is the moment when the debris field question gets answered. If there's a massive cloud of dust and particles trailing behind the nucleus, evidence of the catastrophic mass loss that the acceleration calculation suggests December 19th is when we'll see it. The debris will be illuminated by sunlight, and it will scatter light in ways that make it visible to telescopes across multiple wavelengths. If Loeb is right about artificial propulsion, there will be no massive debris cloud. If the mainstream theory is correct, the debris field will be massive and unmistakable. If we don't see a debris field if the object appears relatively clean, with only a modest coma and no extended trail of particles, that becomes a serious problem for the outgassing hypothesis. Because you can't shed 10% of your mass through explosive outgassing and not leave evidence behind. The particles have to go somewhere, they don't just vanish. Third, spectroscopic analysis will resume with much higher precision. During perihelion, the object was bright, but the observing conditions were difficult. Now, with better geometry and more observing time, astronomers can perform detailed spectroscopy to identify exactly what molecules are present in the coma. Water vapour, carbon monoxide, carbon dioxide, methane, ammonia. Each has a distinct spectral signature. By measuring the relative abundance of these molecules, researchers can infer the object's composition and compare it to solar system comets and the previous interstellar visitor, Borisov. If 3I Atlas shows an unusual composition, an excess of carbon monoxide relative to water, or the presence of molecules that don't fit standard comet chemistry, that would be significant. It wouldn't prove artificial origin, but it would suggest the object formed under very different conditions than typical comets, possibly in a planetary system with chemistry unlike our own. Fourth, trajectory refinements will continue. Every observation adds precision to the orbital solution. By December, astronomers will have weeks of post-perihelion tracking data, allowing them to calculate whether the non-gravitational acceleration is ongoing or whether it stopped once the object cooled. This is critical. If the acceleration ceased after perihelion, that strongly supports outgassing the thrust was thermal, driven by solar heating, and it naturally ended once the object moved far enough from the Sun. But if the acceleration continues, even slightly, after the object has cooled beyond the point where significant outgassing should occur, that's much harder to explain naturally. An ongoing acceleration would suggest a force that isn't tied to distance from the Sun, a force that persists independent of solar heating. That would be extraordinary, and it would demand extraordinary evidence to confirm, but the data will show it, one way or another. Fifth, amateur astronomers and citizen scientists will play a role. One of the remarkable things about modern astronomy is how accessible it's become. You don't need access to a billion-dollar observatory to contribute meaningful data. Backyard telescopes equipped with CCD cameras and spectrographs can track objects like 3I Atlas, measure brightness changes, and submit observations to international databases. The more independent observations we have from different locations and instruments, the more confidence we can have in the results. And that brings up something important. This isn't just a story for professional astronomers to follow in technical journals. This is a story you can follow yourself. The Minor Planet Center publishes updated orbital elements for 3I Atlas. Sky charts showing its position relative to background stars are available online. If you have access to a telescope, you can observe it. If you don't, you can watch as new data gets published and discussed in astronomy forums, preprint servers, and scientific blogs. You're not passive in this. You're part of a global community watching the same object, analysing the same data, debating the same theories, and in December, when the definitive observations come in, you'll know the results at the same time the professionals do. That's the power of modern science. It's transparent, collaborative, and accessible in ways it never was before. So mark your calendar. December 19th, 2025. That's when the mystery either resolves or deepens. That's when we'll know whether 3I Atlas was a conventional interstellar comet with unusually vigorous outgassing, or whether it represents something we haven't seen before, something that doesn't fit our models, something that forces us to expand what we think is possible. And that's not just an academic question. Because the answer to what is 3I Atlas has implications far beyond one anomalous object passing through the inner solar system. It has implications for how we understand the galaxy, how we search for life beyond Earth, and how we prepare for future encounters with visitors from other stars. That's what we need to talk about now. Let's step back from the technical details for a moment and ask the bigger question. Why does any of this matter? Why should anyone beyond a handful of astrophysicists care whether an interstellar comet accelerated at perihelion or whether its colour shifted unexpectedly? Why does 3I Atlas deserve attention when there are wars, economic crises and pandemics demanding our focus? Because this is about more than one object. It's about what that object represents. It's about living in a universe where we're no longer alone in our ignorance, where interstellar visitors arrive every few years, carrying information about places we'll never reach, revealing chemistry and physics from star systems light years away. And if even one of those visitors turns out to be something other than a natural comet, if even one shows signs of technology, of design, of intelligence, then everything changes. Let's start with the scenario where 3I Atlas is entirely natural, where the acceleration is outgassing, the blue colour is ionized, carbon monoxide, and the debris field eventually appears once we have better observing conditions. That would still be profoundly interesting, because it would tell us something fundamental about the diversity of objects floating between stars. Borisov was chemically similar to solar system comets water-rich, dust-laden, ordinary. If 3I Atlas is carbon monoxide-derived instead, that suggests planetary systems form with wildly different volatile inventories, depending on their distance from their parent star, the star's composition, and the dynamics of planet formation. It means interstellar space is populated by objects with chemistry we don't see in our own solar system, representing environments and conditions we can only study through these rare visitors. That's valuable. It expands the library of what's possible. It gives planetary scientists new constraints on how star systems evolve. It provides data that can't be obtained any other way, because we're not sending probes to other star systems anytime soon. Interstellar objects are free samples delivered to our doorstep, carrying information from places we'll never visit. And the more of them we study, the better we understand the galaxy's chemical and physical diversity. 3 objects in 8 years isn't enough to draw sweeping conclusions, but it's a start. If the detection rate continues, if we find 1 or 2 interstellar objects every year, we'll eventually have a statistical sample large enough to characterize the population. We'll know what's common, what's rare, and what's so unusual it demands special attention. Now let's consider the other scenario, the one where 3I Atlas isn't entirely natural, where the acceleration can't be fully explained by outgassing, where the blue colour suggests an internal heat source, where the debris field never appears because the object isn't shedding mass the way comets do. What would that mean? It wouldn't immediately prove artificial origin. Nature is creative, and there could be physical processes we haven't accounted for: exotic ices, internal radioactivity, tidal interactions we underestimated. But it would move the needle. It would make the hypothesis of artificial acceleration less speculative and more plausible. And if that hypothesis survives scrutiny, if it withstands peer review and explains the data better than natural models, then we'd be facing something extraordinary. An artificial object passing through our solar system. A probe, perhaps, sent by another civilization. Not arriving to make contact, but simply passing through, taking measurements, observing, moving on. That's Avi Loeb's long-term research question. If technological civilizations exist elsewhere, and if they're curious like we are, they'd send probes, lots of probes, cheap, durable, autonomous probes that could travel for millions of years, visiting star systems, gathering data, and continuing onward. We're not doing that yet, but we're thinking about it. Breakthrough. Starshot, the initiative to send light sail probes to Alpha Centauri, is based on exactly this logic. Build small, fast, numerous probes and send them to explore nearby stars. If we can conceive of it with 21st century technology, why wouldn't a civilization 1,000 years ahead of us have already done it? And if they have, then the galaxy might be full of these probes. Not communicating, not announcing themselves, just watching, measuring, moving through the dark, visiting star after star over timescales that dwarf human civilization. Most would never come near our solar system. The galaxy is vast, and the odds of a random probe passing close to any particular star are low. But over millions of years, statistically, some would, and we'd see them as fast-moving objects on hyperbolic trajectories, arriving from interstellar space, passing through, and leaving. That's what Oumuamua looked like. That's what 3i Atlas looks like. Not because they're definitely artificial, but because artificial objects and natural objects can look surprisingly similar when observed from a distance. The key is finding the subtle differences, the behaviours that natural objects shouldn't exhibit, the patterns that suggest design rather than randomness. Right now, we don't have enough data to declare 3i Atlas artificial, but we have enough data to say it's worth closer scrutiny, and that's where the future comes in. If this mystery deepens, if December's observations reveal something that doesn't fit natural models, then the scientific community will have to respond. That means allocating resources to interstellar object detection and characterization. It means funding missions like ESA's Comet interceptor, designed specifically to rendezvous with newly discovered objects while they're still inbound. It means building faster, more sensitive sky surveys that can detect interstellar visitors earlier, giving us more time to study them. And it means taking seriously the possibility that some of these objects might not be natural, that we're living in a galaxy where technological civilizations have existed long enough to fill the space between stars with artifacts. That might sound like science fiction, but it's also testable science. If probes exist, they have observable characteristics. They accelerate in specific ways. They reflect light in specific patterns. They might emit signals or heat or other signatures that distinguish them from natural objects. Searching for those signatures is no different, scientifically, from searching for exoplanets or gravitational waves. It's observation, hypothesis testing, and data analysis. The only difference is the subject matter and the implications if we succeed. Because finding evidence of extraterrestrial technology, even defunct technology drifting through space, would be the most significant discovery in human history. It would confirm that intelligence isn't unique to Earth, that life arises elsewhere, evolves complexity, develops technology, and spreads across the galaxy. It would reframe our place in the universe not as alone, but as one voice in a much larger conversation. That's why 3i Atlas matters. Not because it's definitely artificial, it's probably not, but because it's unusual enough to ask the question, and because asking that question seriously is the only way we'll ever get an answer. So where does that leave us? With an object moving away from Earth, carrying data we haven't fully interpreted, with scientists divided between conventional and unconventional explanations, with future observations scheduled that will either resolve the mystery or deepen it, and with the awareness that we're living in a time when interstellar objects arrive regularly enough that this won't be the last one we examine. If you want to stay ahead of this story, to know what December's observations reveal before it hits mainstream media, subscribe and hit the notification bell. Join our community of people who examine data instead of just reading headlines. In the comments below, tell me, what's your best guess? Natural comet behaviour, or something we haven't fully accounted for? I read every comment, and your theories matter more than you know. This is the kind of investigation that takes time, that unfolds over weeks and months, that requires patience and precision. But it's also the kind of investigation that decades from now might be remembered as the moment we started asking the right questions about what else is out there. Thanks for investigating with me.